Now you can, right? You can. Amazing. And the people over there? Yes. Okay, great. Can I have you guys in the back give me a big wave if you can't hear, if you stop hearing me? Thank you, though. I appreciate that too. That's awesome. Hi, good morning. How's everybody doing? Slow notes? Tired? Okay. All right. So we'll see how long my voice holds up. I'm honored to be so trusted that all 4 of my lectures are on the last day. So I'll be also the closing lecturer for the day. So we'll see how that goes. But for right now, does everybody have one of these? If you don't, raise your hand and I'm going to send. Okay. Awesome. Can you maybe distribute them? Would you be okay with that? Yeah, if you see people. Yeah, awesome. Thank you. Oh, and I'm gonna need one, sorry.
Is it possible to like unplug and plug again the HDMI cable? Because it looks pink on Zoom.
It looks pink on Zoom.
Yeah,
yes.
not on the projector.
Okay, and here we go. It started great. We have a pink screen on Zoom. So let's see. And one more time.
Kind of weird.
Would you like more? Do you want me to?
I mean, it's fine if it's big. I think people could still see it.
Yeah.
Let's have a new style now here as well.
Yeah.
It again. So it took her
No, that's okay.
a while to figure that out. Yeah.
Sorry. So what's happening is people on Zoom see a pink screen. So we're trying to fix that.
Yeah. So yeah, I think if you can figure it out, we can.
Thank you. Are you going to be fiddling there while I'm?
No, I'll
Sorry.
No.
Okay, sorry about that, guys. I also just realized that I haven't given Dragan my slides, so I apologize for that, but I'll do that in the break so they can post it. So if you would like to have slides and you don't see them like 2 minutes into the break, just come up and remind me, please. So, all right. So a lot of us have started doing this work in astrophysics and cosmology because of the night sky. I hope that's not exaggeration still to say. So most of you have marveled at a picture like something that looks maybe something like this. This is in the southern hemisphere. But how many of you have looked at the night sky and thought about this? Yeah? All right. Now you always will. All right. So if I go back and forth, this is supposed to be an M-body simulation of our universe, a zoom-in simulation that is matching, if you take a closer look, that blob on the kind of like in the middle on the leftish, to the right of the Milky Way strip, that would be the large Magellanic Cloud. So this is definitely from the southern hemisphere. And then near the dome of the telescope, you see the small Magellanic Cloud. If I go back and forth, you'll see those blobs kind of matching. All right. So this is the universe we live in. This is what's really there. And that's what we're trying to figure out. And of course, there's lots of evidence that all kind of points to a consistent picture that can be maybe summarized in this way. There's a lot more gravity in the universe than we can account for with all the gas and stars that we can see. About 6 times more gravitational force. Elisa was talking yesterday about the evidence for dark matter. So I'm just going to show you my favorite one, because I think this one looks really awesome. And then I may try to pull off some class exercise really quickly. But here is the CMB power spectrum for that content of the universe. So notice the main players there, dark matter, dark energy, and baryons in the right proportions. And the bottom of that little snippet of the CMB sky, the bottom left is the simulated universe that corresponds to that picture. And the top right corner is the real universe, what we see in the sky. So if I erase all of dark matter, I get a dramatically different picture, right? If I were to instead, and I've been asked this question many times in colloquia, if I were to instead substitute all of dark matter with baryons, I again get a dramatically different picture. So this is not like precision cosmology with a CMB. This is like a dramatic change. Okay. So this dark matter, whatever it is, has been around for a really long time throughout cosmic history. And very critically, it behaves as matter. It clusters under gravity, right? So this is the sense at which we know it's matter and not radiation and not dark energy or something else weird in the universe. It behaves like matter. This is also why it's so hard to explain all of the observations that we have from galactic scales all the way to the scales of the CMB and from the local universe all the way to the early universe with something that would be maybe a modification of gravity. It's very, very hard. The simplest thing you can do is just assume that we just haven't detected all the particles that are out there yet. And that wouldn't be that surprising. Only, a decade ago, we made discovery of the Higgs and so on. So dark matter is perhaps the simplest solution to this problem in cosmology. And just a quick question. I'm now debating whether I want to do a real time fiddling with the class code. How many of you have class installed on your laptops right now? Can I see a show of hands? Okay, so here's your homework. All right, I'm going to give you homework. You guys are cosmologists. When you get to your home institutions, first thing you do, you go to Git and you clone class code. This is one of the two main codes that people use these days to evolve the perturbations in the universe in the linear regime. So the stuff you do, and I'll talk a bit about that before you have to run any n-body simulations or anything like that. I promise you, each and every one will want to use this code at some point in your career. All right, it doesn't matter what sub area of cosmology you do. All right, so I'm not going to do the exercise because I would have needed about one person to have class per table, but I might leave you some exercises later on the website. All right, instead, I'm going to dive right in with my introduction, and then I'll tell you about the things that I actually want to teach you that are new. So we're still in the area of the introduction. So dark matter, we know, exists in the universe. It's probably some sort of particle, probably. And so we look for particles in laboratories. Okay, sometimes we build accelerators, but other times we look for evidence of rare events, rare interactions that particles may have with normal matter, which we can measure. Okay, and so for dark matter, we've known since the 60s, we were pretty sure it's there. Something was going on with the rotation curves of galaxies. Since then, we knew that. And for decades now, there's been an effort across the globe in dozens of experiments to actually detect these particles, because if they inhabit the halo of our own Milky Way galaxy, we should be experiencing a wind of these particles going through us at all time in enormous numbers. But we know that they interact with normal matter very, very rarely, so we don't feel it, just like we don't feel neutrinos. They're ghost particles in a sense. But what people do is they build these giant detectors of very, radio pure materials, like, for example, gases like xenon, or sometimes solid state targets. They stick them underground to shield them from everything that could be coming from space and causing signals that we don't really care about. And they surround them by the detectors, very, very sensitive detectors. And they look for evidence of nuclei within these targets recoiling, jittering for no reason at all that we can ascribe to some other event. And then that would be a detection of perhaps dark matter particles from our own Milky Way halo hitting those targets in the detector. And we've been doing this with targets that are ton size, and we're still doing this. We still have not seen any evidence of dark matter that was confirmed. There were claims for detection, but none of them were actually confirmed by experiments. And so what people come up with in these searches is bounds on the weakly interacting massive particle that these experiments search for. And those bounds typically look something like this. So if you've never read a direct detection, dark matter direct detection paper, you may want to Google it or archive it and check out a few of them. You will see a plot like this. And so because of the absence of any interactions that we could see, we have excluded enormous parts of the parameter space. And typically that parameter space is on the y-axis, the cross-section for the interaction with a proton, for example, or maybe neutron, typically with a proton. And then on the x-axis is the dark matter particle mass in GeVs. So when I say a GeV, think proton mass is about 1 GeV, okay? And so colored regions, green colored regions, and everything higher above are disallowed by the fact that we haven't yet seen signals. So I want you to notice the scale on the y-axis, right? These are really, really small numbers. Okay, these are weakly interacting particles. I also want you to notice that the green kind of stops sharply at about 1 GeV and doesn't really cover any masses that are much, much lighter than that. And the reason for that is that we simply have a limitation as to how energetic a particle can be for us to see it as a recoil of a nucleus that it slams into. If it's not energetic enough, it can't impart enough energy, we just can't see it. Okay? And if you want a particle to be living in a dark matter halo of the Milky Way, it just can't be too energetic, otherwise it would have escaped. Right? So there's this fundamental kinematic limit on how low in mass these experiments were able to go so far. All right, so this is kind of the backdrop for all of the cosmological searches for the identity of dark matter particle. We haven't seen a WIMP in laboratory, and if we're looking for a really long time, there are new experiments that are going to push these limits to the blue and maybe to the yellow if we build some new stuff. But that's about the status of direct detection. I'll pause there for a second. Do I have questions? Yeah.
It's more a side comment. If you want to do your exercise with class, I just prepared a Google Collect, and I can send to the people.
That's okay. Let's leave that for the end, but I appreciate it. Okay. Let's leave it for the end if we have time. Do I have questions about direct detection so far? This is a cosmology summer school. I realize you will not get a flavor of things like this. So I figured I'll spend a few minutes on it. But if there are no questions, I'll keep going and I'll circle back around to direct detection a little bit later on. So what are we left with as theorists with this beauty, this proliferation of models that we came up with in the absence of the classical WIMP that was the first thing we looked for when we realized there's dark matter? Okay, so take a moment to take this in and also notice the date on the bottom there. This has been around for about a decade. There are models and paradigms added to this. And a lot of these things, this is like a Venn diagram of how different models, fit within each other and things like that. And a lot of these models target those parameter space of sub-GeV dark matter where we don't have strong constraints from other ways, from direct detection and other things. So in this talk today, in this lecture, I'm not going to go into one by one model. What I'm going to do is I'm going to do a sampling of these things as a cosmologist might and kind of demonstrate to you what kinds of things we're able to learn from cosmology. But this is kind of the backstory. This is like the summary slide of where the theorists' minds go when they think about model building for dark matter. All right, and this is the state of knowledge. This is a slide I maybe made, I want to say like 7 years ago or something like that. It's still the state of knowledge. we have bounds. As Elisa was pointing out over and over yesterday, we have very strong bounds on a lot of things. So chances are, if you work on dark matter, one of your first projects would be place some bounds on this interesting model, see what's allowed and what's not allowed. Okay, we go for discovery, but then we end up with bounds. That's still okay. All right, but dark matter could be a lot of things. We've heard about axions. We've been looking for WIMPs. People talk about dark sectors where you have dark matter hidden from standard model particles, talking very little to them, maybe just gravitationally. And all of these paradigms bear particular imprints, particular signatures. Their microphysics defines the universe as we see it, as we'll see in a lot of different ways. And so we can look for a lot of these things by using cosmological and astrophysical observations. And to an astrophysicist or a cosmologist, this is the question. Okay, and this is grossly simplified, but I want to fill in this diagram. SM stands for standard model, so normal matter, which I also, as a cosmologist, call baryons, to the complete confusion of particle physicists, because I also mean electrons, okay, not just the heavy stuff. I mean everything normal. I sometimes even mean neutrinos, just to add to that confusion. But we want to know, how does dark matter, if at all, interact with normal particles that we know of in the standard model of particle physics? And now, if you're particle physics savvy, this will bother you. This diagram will bother you, because not every process is a 2-to-2 process. Okay, not every diagram has to look like this. But the idea is we want to understand dark matter particle, its interactions with normal matter, its interactions within the dark sector, if there is such thing, its mass, its particle mass, and its spin, right? So this is what we are looking to figure out. And the good stuff is that we have a lot of data, as we've been hearing from a number of people throughout this week. And this is a snapshot from the DS collaboration. I just wanted to make sure that I don't say something wrong, because there's a lot of DS people in the room. But isn't this totally beautiful, right? So we have these massive surveys of galaxies, but we're going to have a whole lot of more coming imminently in this decade. In the decade, you guys are going to be getting your PhDs and applying for postdocs and faculty positions. This is a good time to be doing cosmology and to have a relationship with data, a good, healthy relationship with data. So we have JWST that's taking a look at the very first galaxies, and we've been learning a ton from that. And we, unfortunately, we have to understand galaxies if we want to understand dark matter, because that's the stuff we can see. We have a whole bunch of galaxy surveys coming up, like the Rubin and Roman and Euclid. DESI is already happening, and so on. And then snuck in between these guys, we also have CMB surveys, and those are going to be happening from the ground. So you guys may have heard of the Simons Observatory, but then also what might become its successor, the CMBS4 observatory, and so forth. So we're looking across the wavelengths in various ways. And what all of these data are going to give us are complementary probes of our universe. So I want to pause on this diagram for just a moment to say that, different probes will focus on telling us something about cosmological history and different points in time at different redshifts, but also critically at different scales. Okay, so think about this for a moment. This is a sketch. This is a diagram. Do not quote the boundaries in redshift of this in any way. Just take it in as like a qualitative description of how we tile this space of scale on the y-axis and time on the x-axis. Okay, so have you ever wondered, is there a simple explanation, simple answer to the question of why can cosmology probe fundamental physics? Okay, fundamental physics means small stuff. Cosmology is like the largest stuff we can see. How come, right? And the answer is that when we look at the universe is expanding. It started microscopic, now it's giant. So whatever physics was going on at those really high energies right after the Big Bang and later on in cosmic history, on small scales, whatever those particles that were constituents of the cosmic plasma at really early times were doing, would define what became seeds of structures that we see today. So if you have particles too energetic, too fast, too warm, and so on, they change what the seeds of structures that all of these tracers follow will look like. So they change fundamentally what our universe on large scales today looks like. And the game in cosmology is we set those initial conditions. We talk to particle physicists to play with those initial conditions. And then we play the movie forward, figure out what universe comes out of that, what kinds of galaxies, what abundances of galaxies, what profiles of densities of galaxies, and so forth. And then we try to tie that back into the fundamental physics that we're interested in. So there's a sense in which, the upshot of this slide is there's a sense in which looking at smaller and smaller scales, looking at observables that trace really small scales, you're tracing perturbation modes that are so small that they entered cosmological horizon at earlier times. They became subject to all of this causal physics, to all of this particle physics at earlier times. So there's a sense in which looking at stuff that's so small that maybe we can see it only locally, like dwarf galaxies, you're starting to tap into structures that became relevant at the times at what higher and higher energies, in a sense. So K relates to energy in that way. All right, I'll take a quick digression here, just to mention something I forgot to say. So my slides will be available, and on all of them, I kind of try to put references to papers rather than necessarily cite people by names. If I haven't, feel free to contact me. I'll give you references happily. But those are the things for further reading, okay, instead of compiling the list at the end. The other point that I wanted to make, how many of you have heard of the decadal survey? Yeah? How many have heard about snow mass? Good. Okay, excellent. So white papers from these surveys are like the place to go to pick up references. They're not necessarily the place to go to learn things. Okay, this is where we're selling our science in a very short kind of paper format, but those are the places where you can pick up references or any of the topics that you might be interested in. So I highly encourage that. This was one of the papers from the Astrodecadal 2020. Okay, pausing for a second. Any questions there? This is all introduction so far. Okay, and this is the plan for the rest of the lectures. So I want to start with a really quick recap of computational tools that you might use to do any of the things that I was mentioning, probe dark matter mass, spin, interactions with cosmology. Very, very brief overview, because you've heard of a lot of these things already from other speakers. And then I want to give you examples of how we learn about different properties of dark matter particles from cosmology. And as with Elisa and probably everybody else, this is not going to be a comprehensive overview of everything we think about in cosmology. This is just meant to give you a taste and get you into this business a little bit with some prominent examples that we can understand and unpack. Okay, so this is where we're headed. I mentioned class do this. If you do one thing for your homework other than reading papers, install class and try to run it. And of course, class gives us a way to evolve, like I said, cosmological perturbations in the linear regimes. It solves the set of linear Boltzmann equations. And you can also use CAMP if you're more into that. And their main functionalities in class is that it basically solves the cosmological background. It's a very, very brief lightning overview. When I think of cosmological background, I think, fluid dynamics embedded with gravity, right? So we evolve different fluids dark matter, baryons, radiation, dark energy, using GR, aka the Friedman equations. So this is just really a broad sketch. And one feature of our universe is that the baryons and radiation couple through Thomson scattering. So we have to capture that collision term, the corresponding collision terms, if we're interested to co-evolve these fluids. And then we talk about baryonic acoustic oscillations, which you guys have already heard about. Baryons coupled to photons actually undergo oscillations, undergo sound waves because they have pressure. And so you have to capture that as well. But everything starts with the Boltzmann equation, and then you write things out in terms of the density perturbations delta and velocity divergences theta. These are examples for baryons, and chi usually stands for dark matter. But the beauty is that early universe is a linear system. So it's possible to solve these equations very quickly. Class will run in less than a second on your laptop, right? All right, and here is in real space what the evolution of baryons might look like. So if I haven't convinced you that classes and Boltzmann solvers in general are cool, you also have this tool on your hand, which is called the real space interface. As the time goes forward, you see these oscillations starting, you see gravity pulling things together and so forth. So you can even visualize what all of that looks like. You can do the same for cold dark matter, where the density perturbations do not experience pressure, so they just grow. It's kind of boring. Everything gets rescaled at later times, so that's why you don't get higher and higher peaks in here. But that's the basic idea, right? And then radiation does its own thing and so forth. Okay, so that's linear cosmology. And then you hit redshifts of, 100 or so and later. And then you get to do another problem, which is that now your perturbations have grown enough from that endpoint in that class visualization that I was showing. And you no longer can use linear Boltzmann solvers. So now you go in maybe in real space, you give those perturbations, whatever they looked like at, let's say, redshift 100 or 50 or something like that. And then you tell your computer how gravity works. You chop up your universe into numerical particles and you let it evolve. And you end up with these beautiful nonlinear structures that we can maybe start to compare with the observations that we have today. Unfortunately, I won't show you a link to any particular M-body or hydro simulation code. I'm just going to point you to Frank over there to ask him what his favorite codes are, maybe. But there are a lot of them that are also publicly available that you can run with certain settings, even on your laptop. If you're more theoretically inclined, you will have heard about semianalytic models for structure formation. I'm just throwing some words at you because you're learning a language of cosmology here as well. So you could employ what we call the Praschecter formalism and try to sort of wiggle out what happens with the universe in nonlinear regime. Try to figure out at least like how many halos do I get per given halo mass. And then maybe use that to compare to observations. And if you do that, you have a better handle on what's going on in your theory, but maybe your analytic calculations are not super precise compared to what you can do with simulations and so on. And so often people talk about building these merger trees where, you know, the end point in time is on the right here, and then you have all the halos that have merged to form this final halo that you see in the universe today and so on. And of course, if you're a cosmologist, and that's the face you should have whenever somebody asks about baryonic physics, you have to deal with baryons because those are the things that we actually see. So we have to use them to get at what dark matter is doing. And if you're a cosmologist and thinking about the early universe, then you have to deal with the fact that early on, as the universe started in a big bang, right? It started really hot. Started hotter than the center of a typical star today. So what happens in the center of, you know, the sun, for example, you get synthesis of heavier elements, right? In the early universe, as the universe cooled enough, you got synthesis of heavier elements. But that process didn't get very, very far. We only mostly got helium. So kind of like, what we have in the sun right now. But in order for us to understand how the formation of heavier elements occurred in the process of Big Bang nucleosynthesis, we have to understand all of this nuclear physics. All of these interactions have their rates at various temperatures, which we need to either measure or model in some way and figure all of that out in some, maybe numerical codes to understand, as the universe evolves, how much helium comes out, how much lithium comes out, how much of other stuff comes out. And that's yet another thing we can then compare to observations. All right, here I've put a couple of links to codes that will do this for you, that will compute the Big Bang nucleosynthesis yields of various elements under different conditions. Okay, so if you're interested to play with that, these are some good starting points as well. Okay, and now I want to start with actually getting into how do we learn about dark matter properties using those tools, and how do we try to reconstruct the nature of dark matter. Okay, so yesterday, you heard a little bit about the spin of dark matter particle. And you heard a little bit about the Tremaine-Gunn bound. So the first thing that people did, Tremaine and Gunn, back in the 70s, early 80s, the first thing that people did when they realized dark matter could be a particle, it's definitely there, whatever it is, could be a particle. So what can we tell about it, given that we know things that we know about our universe, given the observations of the universe back in the 70s? And one of the things that people realized is that spin of dark matter particles has a particular interplay with dark matter particle mass and the phase space distribution, aka the velocity distribution and density of galaxies. Okay. So one thing that was realized at that point is that if you want dark matter to be fermions, we know how Fermi gas behaves, we know how fermions behave. You can't pack more than one in one particular state. So if you measure the states, in a sense, of dark matter particles in centers of galaxies where they're tightly packed, where the densities of dark matter are the highest, you measure their velocities, you can actually put a bound on how massive dark matter particles can possibly be if they are fermions, if they have spin 1/2 instead of, bosons and so on. And so I want to unpack that a little bit and then have you do a quick calculation regarding this. So how do we put a bound on dark matter mass dependent on the spin? So we measure line of sight velocity dispersion of dwarf galaxies. So meaning we measure the kinematics in the inner region of these galaxies. By the way, these are typically very baryon poor galaxies. So most of the stuff gravitationally is governed by just what dark matter does. And then from the kinematics of the inner parts of these galaxies, we can reconstruct for every shell, for every distance r from the galactic center, what is the mass enclosed in that distance, okay, from just gravitational force. And when we do this, we make one important assumption, which is that every particle, every star that we see in this galaxy, every dark matter particle, is gravitationally bound to that galaxy. So I'm not going to get some crazy velocity that would mean that this thing would like escape from that gravitational potential well. I'm going to get at most things that move at virial velocities. So once I measure the velocity dispersion, I assume that this galaxy is not like blowing up or falling apart. It's a stable state system. I can reconstruct the mass as a function of radius, and I can build a density profile. Okay, this is a sketch of how it works. And I'm sure observers are cringing over there in the audience, but this is kind of the main idea. So I can compute the escape velocity then as a function of the radius, the distance from the center of the galaxy. Okay, again, just a virial theorem. By the way, throughout this lecture, I'm going to be very loose with factors of 2 and factors of 5, unless they're like in exponents. And so forgive that, but the idea is to get you the scalings correctly. And then I understand that fermions suffer from Pauli exclusion, which means that I can, given their density, I can figure out what is the maximum, what is the velocity that corresponds to how tightly these fermions are packed into that galaxy. Notice that I have to assume what the mass of dark matter particle is there on the bottom. So that M, that's the particle mass of dark matter. Okay, so for a given mass, I want to account for all the particles in this dark matter halo of this galaxy. And that tells me at a given density how tightly packed they are. Okay, so that gives me the Fermi velocity just from the exclusion principle. And then what I can do is I can assert that that Fermi velocity cannot possibly be bigger than the escape velocity. Otherwise, this particle would leave this halo. Okay, are you guys with me on this? Or is this feeling a little Friday-ish o'clock right now? Okay. All right, now take a look at those two equations for a moment. And I'm super regretting that I forgot to post my slides, because what I want you to do next is write down these two equations, please, on a piece of paper the old-fashioned way. You're going to need them.
Why do we have to write these down?
For the quiz, for the graded exam. The graded exam. You don't get credit for the semester. You know, those slides. So what are those letters? I don't know. For the quiz.
I think I can remember this.
Okay.
Also, why didn't you say to take a picture?
We can't use technology here.
I brought my cards. You're gonna kick my ass. Dude.
Okay, 30 seconds more.
Like 98% of the cards are going to be I've never seen them before.
Like,
You can't just.
yeah, I
You
guess.
can't just like.
10 seconds more. That's how time flows in my
As we
unit.
get closer to lunch, I can be the main deck and you can just like start looking through
right.
artifacts.
Do you need more time?
I don't want coaching.
Dude, there's so many combos.
All right, here we go.
Oh my God.
Teamwork time. Please find at least one person that you're sitting next to. I would like to hear people talking as I give you this task. Okay, you learn from me a little bit. You learn the most from your peers. Okay, this is actually research proven fact. You guys will learn the most from your peers throughout your career. So learn to talk to them. Identify your partner, and let's look at this. So what I would like you to do is to use the arguments that I gave you. I'm going to give you 5 minutes, and then we'll take a break after that. If you need to get up and move before, that's okay. Let's use those two equations and estimate the lower bound on fermionic dark matter mass from this Leo 2 dwarf spheroidal galaxy, whose measurements of the density profile and the escape velocity even that's given right there for you are given in these plots. Okay, I would like you to use the measurements at that particular half-light radius that's shown with a vertical line there. And then later on, you can compare your result with the actual paper that gave this measurement. All right, so let's take 4 minutes until 9:56. And I want to hear conversations. Go.
Hi. Okay, what are we doing? So I'm starting by looking at the escape velocity and the density at that radius. What are we supposed to do here? Estimate the lower bound. Estimate the lower bound. Semianalytic dark matter path. So we have this equation. Oh no, we need this. So we need to find this.
To give you the density, yeah, and to give you the flux. We have an equation that relates the two and the.
Yeah. So V
Yeah,
is
you may.
400.
It is the degeneracy is like to 2 for yes for fermions.
I don't know, ma. It was.
Three. You go on. Yeah, do you have Advil?
Advil? No, but I can ask the organizer.
I have gas X.
What's that?
I have gas X.
What's that? Like a Pepto-Bismol on steroids.
Man, you live a great life. You don't have gas X.
I don't know what that is.
Not right now. Yeah, I will use the back.
Do you have Advil? Dude. I don't know if I'm gonna make a good impression.
Do them.
It's his
It's my advisor.
I'll write out the on the.
You really thought he was just asking
I'm
speaker
just
for
writing one number. Yeah.
Would have been better if you went,
I
you have
should
that
give
going
you-
so.
I should give you my presentation.
Bryce would like had a little epilepsy over.
Yeah, what? You have Advil what?
What?
You have Advil.
Over.
But what do I
We
do?
have
I call it them?
right?
Oh.
Okay, so they want you to estimate the lower bound on the mass. The mass is inversely proportional to the velocity. Right?
Yeah.
And yeah, okay, so use that to choose what value you're using here.
But
I'm guessing, unless we
where do
want to
we
do it at a
get-
specific radius.
Where do we get the?
Oh, using the measurements of the escape velocity and the density of the half-life radius. So just
We
use
have
the
this.
values of the half-life
You're
radius.
not doing it.
We have this, right? From the second plot.
Well, no, recent Fermi velocity equal this good.
Oh, you sent me. Okay, so then 40 equals this.
Do you have questions?
Kilometers per second.
You're doing okay? Yeah.
The figures.
Yeah, we don't know what we're.
They're given.
Okay, do you want to run it?
Okay, yeah.
We need to do like unit.
You just need to pull the two values from each graph.
We have to do this unit conversion.
I guess one. Maybe I just. They give it to you in kilometers per
Yeah,
second.
so
Kilometers
Fermi
second.
velocity is
The mass
something
of the sun is
for-
1.988
Right,
times 10 to
knowing
the 33 grams.
that these
Do you
particles,
need
whatever they are, they're
diagnosis?
perfect. They're not.
We need
They're
centimeters
not going to
squared per gram.
microscopic amount. They're in
Yeah, it does
microscopic
also.
amount, but still they're
Desmos is fucking
And so
amazing. Yeah, I can pull it.
Their
we need,
energetics
M to
depends
the
on how
fourth
tight
equals
you
6 pi.
So this formula I haven't derived for you guys, right? The Fermi velocity. You can look it up, remind yourself.
V is going to be
Quantum mechanics, like where does that come from?
times
Comes
10
from
to the
Fermi
fifth
energy and so on.
centimeters per second.
And so that you
Rho
can estimate
is
from
going to
density.
be, what value are you using for rho and solar mass?
To the exponent is for
Parts of the galaxy or whatever system. you're in.
Times the mass of the sun.
So that's like, again, if
And
there
it's
is
in
that density,
kiloparsecs
this is
cubed.
the maximum
That's nice.
velocity.
Okay, thanks.
The maximum velocity.
For that. Okay, kiloparasecs, is it a -3?
You can think of it as like,
I'm putting
every
it all in fucking
more
decimals, are you kidding?
material.
Isn't that
Bump
supposed to be-
up in energy. Right? At the beginning,
Yeah, I'm converting with units right now.
like fill the energy.
Yeah, I
level.
was just.
Why would I use AstroPi when I
So that
can pull up
gives
my,
you
when I can pull out my
an
old
estimate of what that-
undergraduate
What that
notes?
energy is.
Yeah.
Yeah. Yeah, yes,
Okay,
yes, yeah. Okay. Cool. All right, can I have your attention for just a second, guys? Can I have your attention? Thank you. Did anybody get the number? Not yet. Okay, I'm gonna let you finish that off. I think most people are kind of off to a good start. The number you should get, the number I got, presumably that's the number you should get, from crunching these numbers is the mass being bigger than about 170 electron volts. Okay, small number, but that's kind of what you get from this squiggle calculation. If you're interested to see how people actually do it with a little bit more careful approach to modeling what these particles are doing, and employing the virial theorem, employing the Liouville's theorem, and so on, you can check out that paper that's up there on top, but they get a number that's very, very similar to this. So this is order of magnitude estimate, right? And it gets us pretty close to what the answer is from these full analyses. And notice that this is a model independent result. This is a lower bound on the mass of fermions if we want those fermions to constitute halos of small galaxies. Okay, let's take maybe a 7-minute break and be back at 10:05. All right, and I'm here for questions if you have any.
I have a question for this reality. This is
Yes,
great.
Dragan.
I think at least my team is struggling with unit inversions.
Oh yeah,
Yeah, so that's
that's the main thing. Yes, you can, if you don't mind that I'm staring at this just because I have to print this.
No problem. It's about the G factor in the
Yes.
equation. So here, I'm assuming G is 2. Yeah. Oh, okay. But then I thought in general, like, this could be a way to determine the G. But it's not, we're not able to constrain it because we don't know
Yeah.
what that is.
Yes, that's right. So the way you can think of it is if some other way returns a measurement of the mass. Let's say I somehow detect this particle in an accelerator, for example. I produce it, I measure its mass. Then this would be Okay. Okay. Can I have your attention? Did everybody get coffee? You know where. Okay. All right. So a lot of people got tripped up on the units, which is perfectly normal. Get used to it. If you live in cosmology, you live at the intersection of CGS units that astronomers love and the natural units that particle physicists love. So we mix them all up usually. So that escape velocity. So the first thing you should do when I give you a formula or anybody else gives you a formula is you check your units and understand which units the heck are they in, right? Because there's an H bar missing in that Fermi velocity right there. Okay. Does that help? All right. Awesome. So when you recover that H bar, then you will, if I didn't make a mistake in my algebra here, you will get an expression that looks like this. Okay, and you can check that the units work out. And by the way, by the preference of units, you understand whether somebody came from astro training or from particle training. And I'm much more comfortable with CGS. Okay, but this is the formula that you will get, and I'll post the solutions as well. But after the lectures, so the slides should be available now or imminently. Yes, should be available now in a few moments. All right. Okay, so just one more time, the Fermi velocity gives you a sense of the energetics of particles that are packed up so tightly as to have that energy density. Okay, this is a quantum mechanical result. Okay, so if I want to make these fermions denser, I have to bump up some of them to higher levels. I got to give them a kick. Okay, that's the way to kind of heuristically understand it. So I can't do that if these things are supposed to be bound to the halo because they'll escape. That's the entire argument, right? If you want to have fermions dense, you have to account for the fact that that means putting them at a certain energy level, and that's given by the Fermi energy. Okay. All right, moving on from this one, I want to get into talking about the mass of dark matter particles. And I want to focus on what we know from BBN. If you've read dark matter papers that talk about maybe some new model, or if you've heard a talk, people will just like throw this sentence very often, like, oh, from BBN, we know the mass bound. That's a BBN bound on the mass. I used to hate this. Like, this is just used as a phrase, like as a code word that everybody's supposed to understand. But actually the physics that this comes from is much more complicated. There's a lot of nuances in there. So I want to unpack that for you today. And a lot of what I'm talking about in this section will be a lot longer than the spin, than the story about the spin. A lot of what I will unpack will kind of riff off of some of the stuff that Joel was talking about on Monday and Tuesday, or mostly on Monday. So there'll be some points of contact there. It's basically the same story, but I'm going to turn his story of light relics and put it in context of dark matter specifically. All right, so that's where we're headed. And so just one more time, this lecture ends at 10:40. Is that correct?
Yes.
Or 10:30? Were you going to say 10:30?
I think.
Okay. Let me know when you figure it out. I'll
At 10:40.
10:40. Okay, good. So I have half now. All right. So you saw a similar diagram yesterday. Elisa very nicely laid out the kinds of models that you can have in this gigantic parameter space. Notice how dark matter could be something as light as 10 to minus 22 eV to something as heavy as, you know, tens of solar masses. You can't have every model have every mass. There's some models gradient in there as well, but the idea is we're looking for something we really don't know what it is. So we have to search very, very broadly. Okay. So when I talk about BBN and the mass bounds from BBN, they will be hovering around that light dark matter, that purple region in there. Okay, so we're going to be talking keV to MeV mass scales. All right, and we'll see under what conditions these apply. So a very quick summary of the Big Bang nucleosynthesis. As the universe cools down, by around 3 minutes, by around the first 3 minutes, like the book, right? You form all the light elements, or roughly, actually, by around 15 minutes, you finish forming all the light elements that you will build up in the universe primordially before you light up any stars and then make some other heavier stuff, right? And if you rewind the movie of cosmic evolution, you go to earlier times, you go to higher energies. So you go to the right in this diagram. If you're early enough at energies of tens of MeV, okay, you have all these processes going on, all these interactions that I wrote down, and many more, right, that I wrote down in that plot. And notice that these interactions are, involve neutrinos, so they involve the weak force, okay? But as the universe expands, the strength of the weak force, in a sense, is dependent on the temperature of the plasma. So it drops down. And at some point, neutrinos decouple from the rest of the plasma. We call this weak decoupling. Okay, so at around an MeV or so, the interactions that involve neutrinos are no longer efficient. The universe expands too fast for how capable these particles are of interacting with other stuff. Okay, so this is weak decoupling. It happens at about an MeV scale. And that's around the second after the Big Bang. And at that point, the consequence of this decoupling is that interaction that turns protons into neutrons, so normal protons into normal neutrons, all free, right, not bound in nuclei yet, stops, it shuts off. Okay, I no longer can have neutrinos efficiently interacting with stuff. So that interaction right above that 1 MeV mark there cannot flow from left to right anymore. Protons are fairly stable, as far as we know, very, very stable. Neutrons aren't, they decay. If you have a free neutron, after 15 minutes, you end up with like half the amount of neutrons. So their half-life is about 15 minutes. So what ends up happening next is that neutrons then just do their thing. That process just runs from left to right. Neutrons decay. And you have less and less neutrons in your plasma. A little bit afterwards, electron-positron annihilation occurs. So the electrons and positrons start to turn into photons, and they boost the energy of photons in the universe. They give them a little, like temperature boost. They heat them up. But the neutrinos, the only other radiation around at that point in time, doesn't know about it because it decoupled just a little bit before. So neutrinos do not get the boost. And that's where you get that factor, that Joel was deriving for you guys, the difference in the temperature of relic neutrinos and relic photons, okay? Because photons got this boost from electron-positron annihilation. And then after that, you at about 0.1 MeV, you start to really efficiently form deuterium and helium, and then other heavier elements in traces as well. Okay, so nucleosynthesis starts to happen. All right, but by that time, some of those neutrons that were around in the plasma at the time of weak decoupling have now decayed away. So the amount of helium you can get as the most abundant, heavy element is going to be determined by just how much neutrons do you have left by the time you're actually able to form nuclei. All right. So in a sense, and I do not have my other slide. My slide has disappeared in between. In a sense, BBN is kind of a race against time to capture those neutrons and make them not free before they have, all decayed away. Here's a diagram that shows how much fraction of the mass you have in various elements as a function of time. So this diagram, to construct it, you have to know the rates of all those enormous list of interactions that I showed you a few slides ago when I mentioned BBN codes and things like that. So given the expansion of the universe, given the rates of interactions, which we have to measure in some way in laboratories or model in some way at the relevant energies, we can calculate how these processes flow forward. And if you look at the right-hand side of this plot, and all the colored lines, that's about the relic abundance of that element you'll end up with later on. Okay, so the expansion of the universe is taken into account. So flat line just means diluting just because of the expansion, but not diluting because anything's annihilating or being produced or anything like that. So these are the proportions of heavier elements that you end up with. Okay, now you can take those proportions of heavier elements and look at the composition of the universe overall, try to avoid galaxies and contamination from stars and all that nuisance later on. Try to find regions of the universe where you think you're still tracing that primordial chemical composition. And you do that by looking at spectra of distant quasars, where the spectral lines may be imprinted by certain galactic medium or intergalactic medium. And then from this mess of spectral lines, astronomers will infer the content of heavier elements, and will try to measure the total amount of primordial helium, total amount of deuterium, and maybe lithium in traces as well. And these measurements can then be used to understand the process of BBN and what the universe looked like, what the dynamics of the universe looked like at that time. All right, so what about dark matter in all of this picture? Well, dark matter is most often assumed to start off as a thermal relic, okay? So you heard about light relics, and the full name would be light thermal relics. Okay, the stuff left over from the early universe when everything was in equilibrium, including probably dark matter. Okay, notice how big of an assumption this is, right? Maybe dark matter was never in equilibrium with the rest of the universe, but this is a very nice starting point because it gives us predictability, and we'll see that in a second. So thermal relic particles start off in thermal, kinetic, and chemical equilibrium in all of the equilibria with the rest of the universe at early times. And those equilibria are maintained through some interactions. Okay, so particles have to communicate momentum with each other to maintain equilibrium. And so the schematic diagram would look something like this. Chi's represent dark matter, X's represent standard model particles. So let's say electrons and positrons, whatever you'd like. The production would be when you have two standard models coming in, producing two dark matters. Annihilation would be the other way around. And then you could also have elastic scattering, in a sense that you don't change the identities of particles when they undergo scattering. So you have dark matter scattering off of baryonic particle and you end up with the same guys coming out on the other end. So you can have all of these kinds of interactions. And just as a brief reminder, chemical decoupling or the freeze out is when you start to change the number density of one of the species of particles, okay? So you fall out of chemical equilibrium when you annihilate predominantly and you don't produce with the same rate, okay? So the production annihilation must go at the same rate. So these interactions have to go left and right with at the same rate if you wanna maintain the number density of all the particles involved. Okay, if you shut off one direction, you end up with just the other one and you end up building one particle species versus the other. That moment will happen when the rate of inelastic scattering, inelastic would be either production or annihilation, reaches the Hubble rate and drops below the Hubble rate. Okay. So if there's one equation you take from this lecture, it's maybe this one, the gamma. This should be like in your minds when you wake up in the middle of the night, like what's the interaction rate? It's n sigma v, right? And units work out miraculously here because I'm speaking as an astronomer here. So you have the rate of interactions per standard model particle in this case is going to be the number density of dark matter particles times the interaction cross-section times the relative velocity of the particles with which they travel. Okay, when that drops below the Hubble rate, then one of these directions of these arrows will shut off, and maybe I'll end up with just annihilation of dark matter particles. Okay, now all of this stuff is happening during radiation domination. All right, all the freeze outs, all these decouplings, typically in the thermal relic scenario happen during radiation domination, so in the very early universe. Okay, so I know what the Hubble rate looks like as a function of temperature at that point in time, or a function of redshift, whatever you want.
What is the number density of dark matter? It should be a number density of matter or not?
Why is there, so what the question is, why is that the number density of dark matter? Yeah, it depends on which direction, which rate are you talking about, this way or this way, right? So like gamma represents the number density of scatterings per baryonic particle in this case, that what I wrote out. If I wanted the rate of scatterings per dark matter particle, that would be n baryons there. Okay, depends which one you want to decouple. Thank you for the question. Any other questions here? Yes.
Is it always true that the production mechanism stops before the annihilation mechanism, or does that depend on?
Good. You're asking about the order of interactions, whether the production stops before annihilation. Somebody's annihilation is somebody else's production, right? Okay, so there's that. But I was going to get to like, so what can cause this? What can cause this freeze out? So one thing that can cause this freeze out is that the average temperature of your plasma drops below the mass of a particle. Okay, if the temperature of the plasma drops below the rest mass of a particle, you can't produce that particle efficiently. Okay, it's heavier than the energies you have available to build particles. Okay, and so that's the moment when that particle stops being efficiently produced. And it's also the moment when that particle becomes non-relativistic, right? Because the kinetic energies available drop below the rest mass. And by definition, that means I'm entering the regime in which I'm dominated by rest mass, not by the motion. You guys with me on this? This is an important concept. I get some weak nods here and there, but like not much excitement. It's definitely Friday. Okay. All right. So that's chemical decoupling. It's one of the really important concepts in cosmology. Then there's kinetic decoupling. Kinetic decoupling just means that these elastic interactions also shut off. Typically in particle physics, and here's the thing that like nobody ever told me, and then until I figured it out from papers and working on this stuff for years, kinetic decoupling usually happens after chemical decoupling. Okay, in most particle physics models, you'll have dark matter that just first freezes out and then stops interacting in elastic ways, stops scattering in elastic ways. Typically not the other way around. Okay, and there are good physical reasons for that, but model builders all know it, and then astronomers kind of realize it later on. And then if you have no way to exchange momenta, if you have no way to communicate momenta between two different particle species, so none of these interactions happen later on in cosmic history, then you have thermal decoupling. Then the temperature of your dark matter no longer knows about the temperature of the rest of the universe. Okay, and you have two separate species evolving their separate ways. During this time, and here's a nuance, another nuance that maybe some of you have wondered about. During this time, dark matter could have self-interactions. Dark matter particles themselves could still be exchanging momentum and maintain their own internal thermal equilibrium. but you can't use the rest of the universe to understand what their temperature is. Okay, so if you want to know something about the temperature of dark matter, something about the energetics of dark matter particles from the standard model, they have to talk to each other. This is why we so love the thermal relic story. It's very predictive. It gives us a handle on things. Yes.
That implies that the thermal history of dark matter could be different from the thermal history of Earth.
Yeah, so the question is, does that imply that dark matter thermal history can be different from the thermal history of the rest of the universe? Yes, it could be different. Everything we know of, all the particles we know of, and this is like a weak fallback, right? Interact with each other. This is what we know about them, right? Except for dark matter, so far, we haven't seen any non-gravitational interactions. So there's a sense in which it's justified to expect that whatever produced the rest of the stuff also produced dark matter. And maybe in some indirect ways, dark matter does talk to the standard model. Typically, interaction rates for most of the things we deal with in particle physics will increase as you increase energies with an asterisk. Okay, not always true, and cases in which that's not true are really interesting, but most of the time that happens. And so this is why we kind of default to saying like, well, if we go to high enough energies, surely these guys will have been coupled to the rest of the universe, because whatever inflaton decay or whatever reheating produced the rest of the stuff, produced also dark matter and so on. Yeah. But those are assumptions to be aware of, because breaking them leads to interesting research projects. Okay. All right. So just a little bit of thermal here. So here is a thermal distribution there up on top. Okay, if you don't remember this form, open up your, StatMag books and it'll like stare in your face. It's right there at the beginning, I promise you. So don't let it throw you off. So there's a thermal distribution. We know how to compute, in other words, the phase space distribution of particles that are in thermal equilibrium. It looks like that. Plus or minus is a choice between bosons and fermions. Okay. But at the same time, I can then compute the number density of these particles when I integrate out the momenta from this PSD, right? And if you flip through your favorite textbook, for example, Dragan's textbook, you will find these formulas. And there is a difference on what happens when you have relativistic particles in thermal equilibrium, so radiation, versus non-relativistic particles. Okay, so that's the left and right-hand side of this diagram. Notice that in thermal equilibrium, the parameter that controls the distribution is the temperature. That's the one parameter I need, but the dependence on the temperature is different for non-relativistic, read matter, versus relativistic, read radiation. Right? You guys know this. This is T to the fourth and so forth as the evolution with Z and so on. This is where it comes from. All right. And so here is what freeze out of a particle species, a generic particle species, any particle species looks like. On the y-axis, what I'm showing is the number density normalized to the expansion. So a flat line just means I maintain the number density, except things are diluting because of the expansion. So that's the flat line. So that's why T to the third power is there on the y-axis. You guys with me over there? Everybody awake? All right. On the x-axis is a funky version of time, right? It's the mass divided by the temperature of the universe, where mass is the mass of that particle. So what do we see? We see this drop off, okay? And that's a transition from being relativistic to being non-relativistic, okay? Just from StatMag, you get this exponential suppression, that factor, e to the minus mass over the temperature. That's what people call Boltzmann suppression. So you start losing particles when they stop being able to be produced. Why? Because the assumption is that there is that reaction of production and annihilation going in both directions, and then you shut off the production. Okay, so the microphysical interpretation of that Boltzmann drop-off is that I'm starting to annihilate. Okay, nothing in those thermal equations tells me anything about microphysics, but that's how you make that happen. That's how you make thermal equilibrium happen. And that's how you start to fall out of chemical equilibrium, is you shut off production. Yes? Okay. All right. I buy it, but if you don't ask me questions, I'm going to assume everything is like dandy and just keep going, because this is what we do, right? So stop me if you do have questions, to the degree that you're able to absorb anything at this point in time. All right, so notice how that happens when the mass reaches the temperature of the universe. So m/T of order 1, that roll-off starts to happen. Okay, and here is the microphysics interpretation. Okay, if I no longer produce a particle, I start to roll off. But then what's up with that flat region over there to the far right? Okay, so I go from flat, maintaining the particle number density, to starting to lose it, and then again maintain it. So when will I hit that second plateau? When I shut off annihilation. Okay, how do I shut off annihilation? I make the interaction rate drop, annihilation interaction rate, right? I make the annihilation interaction rate drop below the Hubble rate. If I do that, the particles can't annihilate, not because, you know, I can't produce the standard model particles that they would go into, but for a different reason, because they can't find each other. The expansion is too fast. Okay, and that's a moment of freeze out, and whatever is left there, that height of that second plateau, that's the relic density. All right, please prepare your voting cards. I really hope you follow that last slide, because this is going to be all about that. All right, this is how, who's used the voting cards before? This is for my curiosity. Yeah? Nice. Well, yeah, okay. All right, so this is how you use voting cards. You fold them so that you're able to show any particular letter at any given time. This is how you show the letter to your chest. I don't need you to advertise it. I just want you to show it to me so I can see it. All right. So here we go. Are you guys ready? Take a moment, read the question. Do not vote until I tell you to. Do you need more time?
I think particle would take away energy, right?
Do people need more time?
Right.
How are we supposed to do the electoral college if you don't come in?
I gotta hear a yes if you want me to stop and wait for a
We're
second.
supposed to bribe you.
No? And I assume a no.
I also
right.
believe in democracy, but I also.
By the way,
want
this
us
is
to be
E.
Washington, DC.
Okay? You can do this too, but that'll just confuse me. So let's do this. All right, are you guys ready? Let's vote on 3. Put them down. All right, get ready. 1, 2, 3. And I love how everybody listened to me, did this. Okay, I see a complete rainbow here. Perfect. Turn to your neighbor. Turn to your neighbor. Convince them that you're right.
All right.
You have 1 minute. Go.
The universe.
What did you say?
Well, because I do this with research. At least as far as I understand it, whenever, you know, scientists with jargon and crap, when we say temperature of the universe, that's the temperature of the field. So if like the photons, this happened with like the neutrinos, right? The neutrinos, the neutrinos fell out of equilibrium, they weren't coupled to the photons. So they had a different temperature than the photons, but the temperature of the universe was dictated by the photons,
Yeah.
not the neutrinos.
See, that's why I thought that, like, if you have all these particles are in equilibrium, right? These particles have energy, so they decouple and take away. They take away energy with them.
was thinking, depending on whether the particles are being produced or annihilated, and if it's after, then like highly, so then they're contributing protons to the
I think
photon.
that means like they just start annihilating.
And I
But
do
we also kind of, you said the pair production.
Well, she just says, this is what happens when a particle falls out of semianalytic. It doesn't mention anything about it.
I guess.
Let me read the.
Like would mean it's deep.
If it is just a photon part that you're talking about, then it would decrease because it goes like into the scale factor, right?
Yeah, it's always.
It's always decreasing. It's just how fast is it?
I'm like, also, I'm not like any like, I didn't even part for this person, but just by like intuition of energy. I think,
Yeah, yeah.
but I get what you're saying,
Yeah,
like,
yeah.
obviously pair production and relation, that's sort of like how it affects energy, like mass energy.
Exchange mind waves.
Probably
You
not.
can never increase the temperature.
That's what B is wrong.
I
B
agree
is
with
wrong. B
that.
is wrong. And I hear that.
Naughty.
So like when so temperature normally, if everything's chilling, temperature is just gonna go as 1/A, right?
Yeah.
But then if you have something weird happen, then the photon temperature is gonna kind of do that.
Hello? You with me still?
B, kind of,
Do you guys want to revote?
because you're
You
increasing.
don't
what-
go like
relative.
this. You go kind of, you
Looks like-
decrease slow.
The hint is
different.
Give me
like.
some weak notes, nods over here.
Product there. Yeah.
Do you guys have any idea how hard it is to
So-
speak for 2 hours and then get like, sounds like that? I need more energy here.
Right.
All right, let's do Let's see where you're at now.
It's always decreasing.
Prepare your vote cards. Do not vote yet.
I think C is
Please
actually.
do not vote yet. I don't want any correlations. Prepare your cards, please. Let's go on 3. 1, 2, 3.
We could totally be wrong.
Is that?
All right. So I'm gonna give you some hints. Now I have like I have two colored answer. Okay, so you guys have converged to 2 answers. I'm gonna give you a hint. See that beautiful quote from a really good book I know? What happens to G star when a particle falls out of equilibrium? It goes down. Yeah? Imagine that the decoupling is instantaneous. What does that tell me? What does that tell me? What happens to A between before and after? Constant. There we go. You guys see that equation up there?
It's B.
What happens to the temperature? Let's see those cards. 1, 2, 3, go.
If you fix A or not.
Yeah.
Like if you're fixing the scale factor, you're just not even like.
Nicely done.
Depends on what.
All right.
field you're thinking.
Yeah,
And
I'll
we're-
stop there. I'll see you guys at the end of the day. If you have questions, come up.
Okay, but then B.
The one we all decided was definitely wrong.
I'm gonna take a rewatch this. I didn't like that question.
It was a fully worded question, I think.
Temperature of the universe. Ever
Yeah.